Hi there, this is Thermal Physics Lesson 5, Thermal Energy Transfer Extension questions. So these are pretty challenging and quite lengthy. So when I'm going through solutions, you'll probably need to make sure that you follow very carefully, because I'll probably have to, delete and then, clear the screen and keep writing. So, right, there's 3 big questions. What I want you to do is to have a go at them. And so pause, have a go, and then I'll take you through this question. A bicycle and its rider have a total mass of 100 kilograms. The bicycle is travelling along a horizontal road of constant speed of 12 meters per second. The brakes are applied until the bicycle and the rider come to rest. During braking, 70% of the kinetic energy of the bicycle and the rider is converted to thermal energy in the brake pads. The brake pads have a total mass of 0.1 kilograms, and the material from which they are made has a specific heat capacity of 1,100 joules per kilogram per Kelvin. Calculate the maximum possible rising temperature of the brake pads. So in this instance, the kinetic energy of the bicycle and its rider will convert into thermal energy in the brakes. Well, 70% of it will. So first of all, we need the kinetic energy. So kinetic energy is a half mv squared. So 0.5 times 100 times 12 squared, which is 144, gives a kinetic energy of 7,200 joules. Then we need to find 70% of that, so let's times by 0.7. So that gives us 5,040 joules. Then we need to do equals mc theta to find the increase in temperature. So change in temperature is energy divided by mc. So the energy for the brakes is the 5,040 divided by the mass, 0.1, times the 1100. So that gives a rise in temperature of 45.8 degrees Celsius or Kelvin. A change of 45.8 degrees Celsius is the exact same as 45.8 Kelvin. So hopefully that one went okay. Let's try another one. So if you want to pause and have a go. So it might be a tricky one to figure out where to actually start, but the resistance is equal to resistivity times length divided by cross-sectional area. So resistivity, which is what we're after, rho, is equal to RA over L. We know the length of the conductor is given. We need to get the resistance, and we can also get the area. We can get the area from the diameter. So let's get the area first and make sure that you've got this written down. So area is simply pi r squared. So that's pi multiplied by the radius, which is 3.25 to the minus 4 meters. And make sure that we square that value, and that gives an area to 5 significant figures of 3.3183 times 10 to the minus 7 meters squared. So we're going to need that one for later. And then the next part is we've got to find the resistance. So we've got the area, we've got the length, we just need the resistance. So first of all, I'm going to find the energy. So we've got equals mc theta. The energy supplied to the water, that is. So the mass is 2.4 kilograms, multiplied by the specific heat capacity of water, which is given, 4,200, multiplied by the temperature change. So the temperature change is 16 to 100 degrees, which is 84. So that gives an energy supplied of 846,720 joules. And then obviously power is energy divided by time. So we need to do that energy, the 846,720, divided by time of 320 seconds, which gives a power of 2646 watts. Okay, so make sure that's all down, then I'm going to clear the screen and continue. So what we need to do is find the power supply of the plug. So we've got the 2646 watts, which is the power supply to the water. And it's 88.2% efficient. So I'm going to divide by that as a decimal, so 0.882. And what that will do is give us the power of the kettle itself at the supply. So that'll be 3000 watts, or 3 kilowatts. Then what we can do is find the current. So the current is power over voltage. So we've got 3000 watts divided by the voltage. It's in the UK, it's a standard UK plug. So that'll be 230 volts, which gives a current of 13 amps. Which is obviously which is basically the limit of what we can use in a plug. Then from that we can find the resistance. So the resistance is equal to voltage over current. So that's 230 divided by 13, which gives us 17.8 ohms. And then what we can do is put them back into the original resistivity equation. So resistivity is RA over R. Now we can just put the numbers in. So we've got 17.8 ohms multiplied by the cross-sectional area from earlier, 3.3183 times 10 to the power of minus 7, divided by the length, which is the 0.25. And that gives a resistivity value of 2.36 times 10 to the minus 5 ohm meters. So challenging question, a lengthy one. Hopefully it went okay. If not, feel free to rewind and try it again. Let's move on. Again, a very lengthy question. So if you want to pause and have a go at this one. So let's have a look. A lemonade drink of mass 0.25 kilograms at a temperature of 4 degrees Celsius is poured into a glass beaker. The beaker has a mass of 0.3 kilograms and is initially at a temperature of 25 degrees Celsius. We've got the specific heat capacity of the glass and the lemonade. In the first question, assuming no heat loss to the surroundings, calculate the final equilibrium temperature of the lemonade and the glass beaker. So we've seen these ones before, well, something very similar. So we've got the heat loss from the glass, because the glass is obviously starting at a higher temperature and will end up at some lower equilibrium temperature. And that heat energy is going to flow into the lemonade drink because that is colder at 4 degrees. So we've got heat loss from glass. So I'm just going to call that heat from the glass, or heat loss, is equal to the heat gained by the lemonade. So I'll just call it gain lemonade, or gain lemon. So the heat loss from the glass, so we're going to use the specific heat capacity equation, so it's MC times change in temperature. So the mass is, for the glass, is 0.3. Multiplied by the specific heat capacity, 840. And then the change in temperature, so it's going to start at 25 and then come down to some lower temperature, some equilibrium temperature. So I'm going to write 25 minus F. And then in terms of gaining, So we've got the mass of the lemonade drink, which is 0.25 kilograms, multiplied by its specific heat capacity, 4195. 4195. And then in terms of change in temperature, it's going to increase in temperature, so it's going to be the final temperature -4. So final temperature -4. And let's just do some maths. If you didn't get to this point setting out, if you you understand now where you can go from this just to find F, then feel free to pause and finish this question off. So 0.3 times 840 is 252. And then it's 25 minus F. Deal with that in a moment. And then 0.25 times 4,195, which is 1,049. And then it's F minus 4. Then we just need to multiply out. Get all the F's on one side and the numbers on the other side. So 252 times 25 is 6,300. Minus 252 lots of F. Equals 1,049 lots of F. Minus 4,196. So the numbers on the left hand side. So bring the 4196 over, so we should get 10,496 on the left hand side, and take the 252 lots of F to the right hand side to give 1,301 lots of F. So should be pretty straightforward now. 10,496 divided by 1301, which gives a final equilibrium temperature of 8.1 degrees Celsius. Hopefully you could follow that, and that's okay. Let's have a look at part 2. So I'm going to clear this off. So in this one, an unknown mass of ice is added to the now cooled lemonade drink. The temperature drops by 5 degrees Celsius. Calculate the mass of ice that was added. So we need to think about this in terms of energy. So we've got the heat. The heat is going to be lost from the glass and the beaker. And that heat energy that's lost or transferred is going to melt the ice first of all, and then warm the water up that's left behind. So I'm going to try and fit this on because it's quite a lengthy expression to write. So heat loss of glass and beaker. Sorry if that's not the neatest. Heat loss of glass and beaker. That's why I studied physics at university rather than English, so I don't have to write as much. Plus I'd have failed English anyway. So we've got melting ice. I'm just going to call it ice melt. I did okay at English, by the way. I wouldn't write ice melt in a coherent sentence. So melting ice. And then obviously some of that, so we melt the ice with that energy, and then we've got to heat the remaining water. So heat water. Now we can do some maths. So I'm going to try and keep this as neat as I can. So heat lost by the glass, so that's MC theta again. So the mass is, we know, 0.3. We know the specific heat. The change in temperature is 5 degrees Celsius because the temperature drops by 5 degrees Celsius. So 0.3 times 840, the specific heat capacity, multiplied by the change in temperature of 5. And then also I'm going to add the heat loss from the beaker. So we've got the mass of the beaker, so that's 0.25, times the, sorry, not the beaker, I've called it heat loss of glass, heat loss of beaker. That should be lemonade. Apologies. So now we're doing the lemonade, so that's 4196 times 5. So that's the energy that's lost from the lemonade and the beaker. And that's equal to, we've got to melt the ice. I'm going to melt the ice on top. So that's mass times the specific latent heat of fusion, which we've got at the bottom. So unknown mass, M, times L, which is 3.34 times 10 to the power of 5 plus, we've got to heat the water, so that's going to be MC theta. So C for the water is 4,200, which is given here. So it's times 4,200 times the change in temperature, because it's MC theta of 5. Then we can do some maths. So if we add on the left hand side, there's the 0.3 times 840 times 5 plus the 0.25 times 4196 times 5 gives us 6,505 on this left hand side. Equals, and on the right hand side, we've got this one at the top, plus, I've already got the plus there, the MC theta. So we're going to factorise this. So we're going to pull the M out, and then I've got 3.3 times 10 to the 5 plus 4,200 times 5. So I'm just going to write this out. So I've got 3.34 times 10 to the 5 plus the 4,200 times 5, not times 5, times the change in temperature, 3.1. So 4,200 times 3.1, because it's going to go from 0 degrees Celsius up to 3.1 Celsius, because the initial temperature was 8.1 and it dropped by 5. So yeah, that is 3.1. So 3.34 times 10 to the 5 plus 13,020. Then we just need to do 6,505 divided by the number on the right. So that would leave you with a mass of 0.019 kilograms. So we got there in the end. Hopefully that's okay. Be very careful with this bit. And if you can't follow it, let me know, I'll record it again. Alright, but thanks for watching anyway. I hope them questions proved challenging. And I'll speak to you on the next one. Thank you.